There is something happening right now inside every atom of your body that your brain was never built to understand, not because you aren't smart enough, but because the rules down there are genuinely different from anything your ancestors ever needed to survive. And here's what's strange. Physicists know what quantum particles do. They just cannot tell you why without the math dissolving into something that sounds like philosophy. So let's ask a different question. Not what is quantum weirdness, but why does reality seem to refuse the answers we expect? Because it turns out the mystery isn't magic, it's a limit. And limits, once you see them clearly, are more fascinating than any ghost story. Start with something you probably think you know. An electron, a particle, tiny, solid, located somewhere. That picture feels obvious. It's the picture your textbook drew. It is also wrong, and not in a small way. An electron, when no one is looking, and by looking, physics means something very specific, does not have a position. It has a spread of possible positions, each with a different probability. This is not a measurement problem. It's not that the electron is somewhere and we just can't find it. The electron genuinely isn't anywhere specific until something in the universe forces it to choose. Now here is the experiment that makes this impossible to dismiss. Fire electrons, one at a time, through two narrow slits cut into a barrier. Behind the barrier is a detection. Pause and predict what happens next. If an electron is a particle, what pattern do you expect to see on the screen? Two bands, one for each slit. That's the obvious answer. That's what a particle would leave. What actually appears after thousands of electrons have landed individually one by one is an interference pattern, alternating stripes of high and low density, the kind of pattern you only get when waves overlap and cancel each other. The single electron, with nothing else in the apparatus, passed through both slits simultaneously and interfered with itself. It was in a superposition of paths, not split across locations like two pieces of the same thing, but existing in a state where both paths were simultaneously valid. Here is where it deepens. Put a detector at the slits to measure which one the electron actually went through. The interference pattern disappears instantly. Two bands return. The act of measuring which path was taken collapsed the superposition into a definite single choice, and the wave behavior vanished with it. The universe, in some sense, behaves differently, depending on whether it is being watched. This is not a metaphor. It has been tested, refined, and confirmed across decades of experiments. The double-slit experiment is not a quirky demonstration. It is the front door of quantum mechanics. This leads directly to a misconception that even science communicators repeat too loosely. People say the electron is in two places at once. That phrasing is doing real damage. The electron isn't splitting itself across locations like a divided piece of bread. Superposition means multiple outcomes are simultaneously valid, with none of them being more real than the other, until interaction forces a single answer. Think of it less like a coin spinning in two places, and more like a question that hasn't been answered yet. The question is perfectly real. The answer just doesn't exist until someone asks. Now, physicists still argue about what actually happens during that moment of measurement. Some say the wave function collapses into one outcome. Some say all outcomes happen simultaneously in branching parallel realities, what's called the many worlds interpretation. Others hold positions in between, but here is what they all agree on. The predictions, the numbers, the experimental results are identical regardless of which interpretation you hold. The philosophy is unresolved. The physics works anyway. That tension, quietly, says something profound about the limits of what any theory can claim to explain. Now here's where it escalates further, because superposition isn't the strangest part. Entanglement is. Two particles interact, become entangled, and then separate. You send one to the other side of the planet, measure the first particle, and instantly the second particle's state is determined, faster than light could have traveled between them. Einstein hated this. He called it spooky action at a distance, and spent years trying to prove it was a sign that quantum mechanics was incomplete, that hidden variables must be carrying the information, like instructions sealed in an envelope before the particles parted. In 1964, Physicist John Bell designed a mathematical test to check whether hidden variables could explain the correlation. Over the following 20 years, labs ran the experiments, and Einstein lost. The correlations between entangled particles are stronger than any pre-programmed hidden instructions could ever produce. The connection is real, and it has no classical explanation. But here is the critical nuance. This connection cannot send information. You cannot use entanglement to control what the other particle does. You get a correlated result, but only after comparing notes through a normal channel. There is no faster-than-light communication. Relativity is not broken. What breaks is the intuition that two separated things must be independent. This is a simplified explanation to make the core idea intuitive. The full mathematics of Bell inequalities goes considerably deeper. Pause and predict what happens next. If quantum particles behave so strangely at small scales, why don't tables and chairs and human bodies behave the same way? The answer is decoherence, and it is one of the most underrated ideas in all of physics. When a quantum particle interacts with its environment, even one stray air molecule, one passing photon, it begins to entangle with that environment. And the larger the system, the faster its quantum behavior gets washed out by the noise of countless interactions happening every fraction of a second. By the time you have billions of atoms behaving together as a solid object, the quantum weirdness has averaged out into something that looks exactly like classical physics. The table doesn't hover in superposition, not because quantum rules stop applying, but because the environment has already done the measuring billions of times per second, and averaged the results into something stable and ordinary. The world you see is quantum mechanics running at enormous scale, pretending to be Newtonian. That pretense has a name, the classical limit, and it is not a failure of quantum theory. It is quantum theory producing a new layer of reality from its own rules. Now here is a misconception worth clearing before it calcifies. People often imagine that Heisenberg's uncertainty principle is about shaky measurement tool, as if better technology would one day let us measure both position and momentum of a particle with perfect precision. It would not. The uncertainty principle is not about bad instruments. It is a statement about the mathematical structure of waves, and particles at small scales behave like waves. You cannot measure the exact frequency of a wave that only lasts for an instant. The precision of the frequency depends on the duration of the position, and momentum carry exactly this relationship. The more tightly you pin down one, the more undefined the other becomes, not because of disturbance, but because definiteness in one property is mathematically incompatible with definiteness in the other. The universe enforces this without apology, and no engineering breakthrough will change it. Two real-world anchors are worth holding here, because they show that these abstract ideas have already shaped the physical objects in your life. Your GPS device is corrected every day for the effects of relativity. Satellites moving fast through orbit experience time running slightly slower than clocks on the ground, while sitting in weaker gravity makes it run slightly faster. Without those corrections, your phone's location would drift by kilometers per day. Time itself flows at different rates depending on your speed and position in a gravitational field, and consumer technology is built around compensating for that. Muons make the same point. These particles are produced when cosmic rays hit the upper atmosphere roughly 10 kilometers above your head. Their average lifetime is about 2.2 microseconds. Classical physics says they should decay long before reaching the ground. They don't. Because, from the muon's perspective, moving at nearly the speed of light, its own internal clock runs slower relative to ours, and it survives long enough to be detected at sea level. Time dilation passes through you every moment of every day. And then there is the quantum layer itself, the transistors inside every phone and computer, the lasers that carry data through optical fiber, and the MRI machines in hospitals. None of these technologies would exist without quantum mechanics. The 11 decimal place precision of quantum predictions is not an abstract boast. It is the engineering tolerance of the modern world. One final misconception deserves its moment. People often hear the word quantum and conclude that reality is random and therefore unknowable. that anything can happen, that physics at small scales is chaos wearing equations. Quantum mechanics is one of the most precisely tested theories in the history of science. Individual measurement outcomes cannot be predicted, but the probabilities of those outcomes can be calculated with extraordinary accuracy. The randomness is real and irreducible. The statistics are not. Quantum mechanics does not hand you chaos. It hands you a precise map of probabilities and lets the universe pick from that map without asking you first. And now, after all of that, the double-slit, the measurement problem, superposition, entanglement, decoherence, uncertainty, dilation. The question planted at the very beginning finally has its answer. Why do quantum particles refuse the answers you expect? Because your expectations were built for the middle layer of reality. For rocks thrown, rivers flowing, fires burning, quantum mechanics is the basement of that building. Relativity is the architecture of its outer wall. Neither layer was designed for human intuition, and that is not a failure of physics. It is physics being more honest than intuition ever was. Every mystery examined tonight turned out to be the same thing, wearing a different mask, a limit. The limit of what information can be extracted without disturbance. The limit of how long quantum behavior survives contact with the world. The limit of what speed and gravity do to time. The universe is not hiding its secrets in random acts of strangeness. It is simply operating at a precision your senses were never built to reach. And the distance between its precision and yours is what we have always called mystery.